Hello, this is Calculus 1, MAT221. This is Mrs. Johnson, and we're in section 4.8 talking about antiderivative rules. In this particular video, we're going to go into more depth into the backwards or the antiderivative rules analytically. And they really, most of them come from a little bit of intuitive thinking about thinking backwards from our derivative rules that we already have. So knowing those 26 rules that you already know, hopefully you'll recognize how to find the antiderivative of most of these functions. So now we talked about derivatives and examined the relationship between the function, the first derivative, and the second derivative, and we're thinking backwards here. Our goal is to find a function that's the antiderivative of the given function. This is called the general antiderivative. Now we know the differentiation formulas, and we are in the position to now find the explicit expressions for these general antiderivatives. Remember, the general antiderivative is, if you are given a derivative curve, it would be the curve that came from. The derivative that is given to us is the derivative of some antiderivative. Now in these particular slides, I'm using the derivative notation and little f notation, as opposed to in the last PowerPoint I used the f of x notation for the derivative and the capital F for the antiderivative function. Both are correct notations. We always think that the derivative function that is given to us that will have an antiderivative function that is the family of functions differing only by a constant. We write this using this notation, by the way. If you look at this notation is called the indefinite integral. It tells us to find the general antiderivative of what follows. And if you look, whenever you see this elongated squiggle, actually we'll talk about this when we get into rectangular approximation methods, why Newton used this symbol. It's called the indefinite integral symbol, and what it's telling us is find the general antiderivative of the function that follows. So in other words, the function that follows is always going to be a derivative function, no matter what the notation says, whether it says prime or not. If a function sits next to this integration symbol, this indefinite integral symbol, the function that sits next to it must be a derivative of some function. And that function is the antiderivative function, which is the family of curves whose derivative is given by this function right here. So if I said to you, find the general antiderivative of the following functions. So if I said to you, the derivative of a function is e to the x. Using your knowledge of derivatives, what function has a derivative of e to the x? Of course we know this one. E to the x is one of the few functions that is its own derivative. But we always add a plus c because there might have been a constant attached to the function that gave us a derivative of e to the x. This is the general antiderivative of e to the x. What about 3x squared? Well, we did this in the last video. We know that that's equal to x to the third plus c, because the derivative of this function, x to the third plus c, will give us 3x squared. Again, it is the family of curves that all differ just by a constant, that all have x cubed as its leading coefficient, or its leading term. We did this one in the last video too. If I said to you the derivative of a function is 1 over x, then we know that the function must have been the natural log of x function, because we know the derivative of the natural log of x is 1 over x, plus perhaps some constant. All right, so those were easy. We got those from the last video. But you can really see how important it is that you know and recognize the derivative functions in order to think backwards for antiderivatives. Remember, a specific antiderivative or an initial value problem, right, was known if we know some particular information about the function, then we can find the value of c, and we can actually solve for the one and only one function that meets that criteria. That's when we find a specific antiderivative, and if we have what's called an initial value problem. We also found the general antiderivative for x to the n. Remember, we said that the derivative, if I have a derivative of x squared, that came from a function whose original function must have been 1/3 x to the third. If I had a derivative function that was x to the third, that must have come from 1/4 x to the fourth plus c. And we came up with this general formula for the power function. This is called the shortcut for antiderivatives for the power rule. And it was x to the n plus 1 over n plus 1 plus c, or 1 over n plus 1 times x to the n plus 1 plus c. So we're adding 1 to the exponent and dividing away by that same exponent so that our coefficients end up correct. So we have a bunch of rules now. Let's look at some others. Let's do some examples. Let's find the antiderivative of these functions. These are pretty easy using that rule. 1/10 x to the 10th plus c. 1/7 x to the 7th plus c. Be careful with negative exponents. We have 1 over -10 x to the -10. And we can remember the rule only applies when n does not equal -1. We can't have 1 over x because remember that has a derivative of natural log. But every other power function we can write in this form. W to the -6 would be 1 over -5, W to the -5 plus C. Again, adding 1 to the exponent and dividing by that same exponent. 1 over 1 plus 1.6 x to the 1.6. 1 over 0.2 x to the 0.2 plus C. Right, so this is just using that general rule for antiderivatives for power functions. Let's look at some other ones. Now, if we knew that the derivative function was x to the 7th, and we also knew that f of 0 equals 12, this is an initial value problem, a specific antiderivative. So I take the general antiderivative first using the power rule going backwards for antiderivatives, and then substituting 12 in for y and 0 in for x. So in this case, my constant equals c. So my answer is the one and only one function, f of x equals 1/8 x to the 8th plus 12. So let's put some more of these other rules and see if we can go backwards from what we know. What about if we just had a constant? If I wanted to take, remember this symbol means I want to take the antiderivative, the general antiderivative of a number. Notice that must come from a linear function because we know that the linear function, the derivative is just whatever the slope is or whatever that constant is in front of the x. So this is a special case of the power rule where we're going backwards from a number. We get x, k times x plus c, where k is that constant, that number. Again, this would make sense because the derivative of a linear function is equal to the slope of the line, and it's just going to be a number. So if x is to the first power, the derivative would be the coefficient or the number. So let's do an example. If I asked you to find the general antiderivative of 2, you would say 2x plus c. If I asked you to find the general antiderivative of -5, you would say that is -5x plus c, using this rule. This is a special case of the power rule called the linear rule for antiderivatives. So when we're just given a number, we can go backwards by just tacking on an x. This is the sum and difference rules for antiderivatives is just like the sum and difference rules for derivatives. If I take the antiderivative of the sum or the difference of two functions, we simply take the antiderivative of the first and then add or subtract the antiderivative of the second. Remember, this indefinite integral symbol means find the general antiderivative. Also, I have the constant multiple rule for antiderivatives, which is similar to the constant multiple rule for derivatives. If I have a constant multiplied by a function, I can take that constant and pull it out to the front and then take the antiderivative of the function. So let's do a couple of examples using these rules in conjunction here. I want the general antiderivative of this function. This symbol indicates that. So I'm going to pull out the 7. Then this becomes 1/5 x to the 5th. I'm going to pull out the -8. This becomes 1/-4 x to the -4. And 9 is the linear rule, becomes 9x. And then I just add a c. Simplifying, I get this. Another rule we just saw was the general antiderivative of e to the x is equal to e to the x plus c. If I have the general antiderivative of e to the kx, just as this has a mini chain rule, this has a mini antiderivative rule here too. The antiderivative, the general antiderivative of e to the kx is equal to 1 over that constant multiplied by e to the kx plus c. The antiderivative rule for exponentials, if I have an exponential function, is equal to 1 over the natural log of the base of that function multiplied by a to the x plus c. Again, this is similar to the derivative formula for exponentials, where we multiply by the natural log of the base. Here we divide by the natural log of the base. So let's do a couple of examples. If I said to you, what is the general antiderivative of e to the 5x? We would use this rule. E to the 5x would be 1/5 e to the 5x plus c. If I asked you for the general antiderivative of 5 to the x, I would use this rule, which would be 1 over the natural log of 5 times 5 to the x plus c. Antiderivatives for 1 over x, we already saw before, that is equal to the natural log of x. Actually, we could even say this is the 1 over x is equal to the natural log of the absolute value of x. Sometimes that's done too. But often what they'll do here is they'll put the caveat here that x has to be greater than 0, because remember, we can't take the natural log of a number unless it's greater than 0. So here are some examples. Here are some examples. The antiderivative of 5 over x dx would be the same thing as 5 times 1 over x dx, which would be 5 times the natural log of x plus c. The general antiderivative of 1 over x would be the natural log of x. The general antiderivative of 3x to the 4th would be 3 times 1 over 5x to the 5th. And the general antiderivative of a number is just negative x in this case, plus c. Let's try another one. And we get e to the x plus the natural log of x plus 1 over the natural log of 7 to the x, plus c. This is using all of our rules. Here we have 5 times 1/4 x to the 4th minus x to the 3rd plus 7 over 2 x squared minus 1 over the natural log of 5 x to the 5th plus c. Again, just examples of using these rules. Now, this is on a worksheet that we have in Blackboard that kind of goes backwards to all of our derivative rules. It's a place that you can use shortcuts for all of these shortcut rules. And in the next video, I'll go over some of these examples from that worksheet. They all come from the derivative rules that we had in Unit 3 when we did all of our derivatives. Notice these first few we've done already. Here, the derivative of sine, the derivative, the antiderivative of cosine, and so forth.